Good afternoon. We live in turbulent times which show us that no status quo is forever. Among other things, this talk demonstrates how latest advances in science and technology question a paradigm in gravitational field modeling. Let me start with an introduction. External spherical harmonic expansions date back to Legendre and are still the most popular parametrization of the gravitational field. The convergence domain of the series is the space above the minimum Brillouin sphere, depicted by the red circle in the figure. Nevertheless, we commonly use these series inside the bounding surface. Some researchers justify the analytical downward continuation by the Runge-Krarup theorem, but the latest progress indicates against this practice. In this talk, I discuss the related mathematical theory, a brief historical account on the convergence-divergence issue, and numerical experiments on the Moon. I move on to the mathematical theory. Perhaps the most fundamental equation in the gravitational field modeling is the Newton integral in the gray box. It allows evaluation of the gravitational potential V by integrating over the density ρ weighted by the inverse of the Euclidean distance L. The variable topography of the gravitating body Rs appears in the integration limits. I expressed the Newton integral in the spherical coordinates for later purposes, where r is the radius and omega substitutes the spherical latitude phi and longitude lambda. We can convert the Newton integral into the internal spherical harmonic series in the gray box in 5 relatively easy steps. The series composes of 2 double summations, each running over the degree n and the order m. The first term represents the gravitational effect of all masses below the blue sphere passing through the computational point. The second term is the gravitational effect of all masses above the blue sphere. In both summations, we can clearly identify the powers of the radially dependent ratios, the spherical harmonic functions y and m depending on omega, and the spherical harmonic coefficients CNMO or CNMI. Importantly, the spherical harmonic coefficients are not constant and change whenever the position of the computational point changes. We can determine these coefficients only by forward modeling, that is, from the knowledge of the density and topography of the gravitating body. For the computational points above the minimum Brillouin sphere, the second term of the internal series vanishes and we obtain the external series on this slide. Notably, the spherical harmonic coefficients C and M are now constant and define physical properties of the gravitating body. We can determine these coefficients either by forward modeling or we can estimate them from gravitational field observations using least squares or from analytical solutions of the boundary value problems. It is exactly this series and its spatial derivatives that I called the popular parametrization of the gravitational field. These are routinely and perhaps incorrectly used within the minimum Brillouin sphere. That brings me to a brief historical account on this matter. Many researchers have discussed this procedure generally known as the analytical downward continuation. I have read at least 24 publications on this topic and found it very confusing. However, I could clearly identify two opposing camps within our community. The first camp is the paradigm which has been pushed mainly by theoreticians since 1960s. Their main argument is the Runge-Krarup theorem, a part of which states that any function phi, harmonic and regular outside the Earth's surface, may be uniformly approximated by functions psi, harmonic and regular outside an arbitrarily given sphere inside the Earth, and so on. It was the geodetic giant Helmut Moritz who highly popularized this theorem. I took a quote from his famous textbook titled Advanced Physical Geodesy, where he in particular writes, "It is always possible to consider the Earth's external potential as a convergent potential." Other scientists took the theorem for granted and studied its theoretical and even numerical consequences. We can say that the Runge-Krarup theorem, together with its big-shot proponents, turned the analytical downward continuation into an undeniable practice in geodesy, geophysics, and planetary sciences. The second camp is the paradigm shift. Its attitude is more conservative and perhaps based on the hesitation of Jekeli, who wrote back in the 1980s. It should be noted that the Runge-Krarup theorem is an existence theorem. It guarantees only the existence of an approximating function and does not provide a method to find it. In the past decade, at least 4 research groups have employed newest high-resolution topographic and gravitational datasets on different planetary bodies. They all reported failures of the analytical downward continuation. In addition, Ogle and Kostin, together with their collectives, worked out purely analytical proofs and ended up with the following statement. The probability that the spherical harmonic expansion of the gravitational potential will converge in free space beneath the Brillouin surface is 0. The shift in the paradigm in fact points to the basic textbook knowledge stating that the external spherical harmonic series are guaranteed to converge above the minimum Brillouin sphere, but there is no such guarantee inside this surface. I contributed to the paradigm shift in a special work that got published in 2021 on the Moon. This planetary body is a perfect candidate for demonstrating possible issues with external series. Namely, its low flattening is consistent with the spherical approximation, the topography is complex, and the gravitational field is static. The topography of the Moon has been mapped by the Lunar Reconnaissance Orbiter depicted on the left since 2009. The GRAIL satellite mission illustrated on the right accurately measured the lunar gravitational field. I now use very unique NASA datasets from these satellite missions in 2 numerical experiments. The first experiment is a global analysis. I compared the internal and external spherical harmonic series for the radial derivative of the potential and examined them at the sphere of radius 738 kilometers, that is 10.2 kilometers beneath the minimum Brillouin sphere on the Moon. The spherical harmonic coefficients were calculated by my own rigorous forward modeling approach. For this purpose, I utilized a terrain model from the LOLA sensor with an angular resolution of 1/56 arc degrees and a constant density of 2550 kg per meter cubed. All gravitational fields in this experiment were based on forward modeling. They correlate with the realistic counterparts, at least in high frequencies. We now look at the comparison in the spatial domain. The gray box highlights the two computed quantities. The red external series is valid only above the minimum brilliance sphere and was downward continued in this experiment. The blue internal series is exact inside the enveloping sphere. I calculated the maps on the right between the degrees 150 to 600. Both fields have low amplitudes in the Procellarum Craterane area on the near side and in the South Pole Aitken Basin on the far side. We can observe higher amplitudes in the lunar highlands or mountains. Clearly, the maps and the statistics show that the blue internal series results in significantly smoother gravitational field. For the spectral domain comparisons, I calculated the root mean squares of the spherical harmonic coefficients in the gray box. The red formula is consistent with the external series and the blue expression with the internal counterpart. They give us information on the signal strength as a function of spherical harmonic degree. The graph on the right shows the two indicators up to degree 1800. The signal power of the blue internal series nicely asymptotically decreases as the degree increases. In contrast, the signal power of the red external series increases from degree around 700, indicating its failure when used inside the minimum brilliance sphere. The second experiment is an analysis along the Grail orbit. I considered one 24-hour segment on December 14, 2012 and compared three types of line-of-sight gravitational accelerations. The observed accelerations were derived from the Grail Level 1b and Science Orbit data. The other two accelerations were forward modeled with parameters identical to those of the global analysis. To avoid underflow of the Legendre functions, I used the X-number procedure in the spherical harmonic synthesis. To clarify, the line-of-sight acceleration is the difference of gravitational gradients at the two Grail satellites, but projected onto the unit intersatellite vector b. The gray box summarizes its three distinct types. I calculated the black observed accelerations from the intersatellite range ρ, position vector x, and their time derivatives. These are completely independent of any mathematical parameterization. The spherical harmonic-based accelerations were synthesized by the red external series. I recall again that the convergence of the series is guaranteed only above the minimum brilliance sphere. The third set of accelerations was generated by the blue Newton integral based formula. The symbols HT and HU stand for isotropic kernels. BR, B phi, and B lambda are the components of the vector B, and alpha is the direct azimuth. The blue accelerations are exact everywhere in 3D space. We now look at the most important plots. The Grail satellites orbited the Moon at an extremely low altitude that day, as seen on the left. the spacecraft oscillated around the minimum Brillouin sphere from -7 to +9 kilometers. The figure on the right shows the signal power of the free accelerations as a function of frequency. The signal powers are almost identical up to about 0.20 Hz. Beyond this frequency, the powers of the observed accelerations and those from the integral formula tend to decrease. However, the signal power of the accelerations from the external spherical harmonic series has an increasing trend. We now examine the coherence spectra depicted on the left. The accelerations from the integral formula highly correlate with the observed ones. The corresponding blue coherence is higher than 0.7 up to about 0.23 Hz, and then it decreases as the measurement noise leaks in. In contrast, the red coherence between the observed and spherical harmonic based accelerations drops already at about 0.17 Hz. I interpret this degradation in the coherence as a failure of the spherical harmonic representation because half of the computational points are located inside the minimum Brillouin sphere. To further support this claim, the figure on the right shows high-pass filtered accelerations. This is a truncated segment around the third orbital minimum. Clearly, the high-pass filtered accelerations from the Grail observations and those from the Newton integral agree very well, while the external series provides highly variable and erroneous values. I also inspected segments around the other orbital minima and found the very same behavior. We have to stop the story now and go to the conclusions. In this talk, I presented a theoretical summary, a historical account, and numerical experiments on the use of the external spherical harmonic series inside the minimum Brillouin sphere. For decades, the paradigm in our community has been the analytical downward continuation without questioning. However, studies based on the latest developments in fundamental sciences and technology strongly discourage this practice. The shift in the paradigm may have crucial implications for gravitational field modeling and its applications. For example, we may ask whether constraints in the form of power laws are realistic or whether geophysical interpretations make any sense. If the topic interests you, this QR code will take you to the PDF files of this presentation and the study from 2021. So what do you say? Would you trust the numbers calculated by external spherical harmonic series inside the minimum Brillouin sphere?